Welcome to solverfy.
Okay, so in this question, we're talking about photon with a wavelength of 0.1 micrometer. So let's see where this problem goes. E is equal to hc over lambda. And then we were told lambda is 0.1 micrometer, so it's 0.1 times 10 to the minus 6 meters. And what we want to do is do h times 0.998 times 10 to the 8th, and then divided by 0.1 times 10 to the minus 6. Is that really what they asked for? What is the energy of a photon? And I guess I should put it in EV, so 1.602 times 10 to the minus 19. And so I divided it by E, the charge of the electron, and I get, how many sig figs should I do it to? 2 sig figs. So then I get 12 EV for A. And then for B, we want to know that if we're accelerating electrons through some potential difference, and we want them to exhibit their wave nature if they're going to pass through a pinhole of that size, and then what's the speed of the electrons. Oh, that's kind of interesting. And so we want basically we want their de Broglie wavelength to be on scale with the size of this pinhole. So we because in general, whenever the whatever dimensions the de Broglie wavelength is, that's where you'll see the wave effects. And so for normal matter, that becomes very, very small. So we don't generally see the wave effects. So what we're going to do then is do lambda, is use this for our lambda, and then set that equal to h over p. And okay, and then, okay, we want to know the potential difference. Okay, so we have lambda, we have h, so we can get p, so you can get that p is equal to h over lambda. And then p, but then so thinking about sending a, let me back up. So this is the p that we need to get. So we can calculate that by just dividing this number by, or dividing h by this number. But then to associate that with the voltage, we need to figure out how many, what potential difference would get an electron to that potential difference, or excuse me, to that momentum. And so basically through energy conservation, you can say you could turn the energy gain through being accelerated through a potential difference, which is E delta V, into kinetic energy, and that's P squared over 2M. So then if you take this equation and solve for V, you just want to take this whole thing and divide it by E. So delta V is equal to P squared over 2M. I wonder if A will end up connecting. We'll find out. So P is plugging in this for P. Then we get H squared over lambda squared M E. Oh, and then times 2. Can't forget this too. And so far, I'm not quite seeing the connection, but that's okay. I'm going to go ahead and start calculating. And then again, I'm going to use this for my lambda. I'm going to pause the video while I do this calculation. I got 0.1 millivolts. And I'm just going to double check I didn't forget that factor of 2 lambda squared ME. Great. So now what I want to do is get their speed. So getting the speed, that's just, let's see, that's just calculating MV. And so I guess let me start labeling this actually. So this is all for B. Oh, I did label them. So P is MV, V is P over M, P is equal to H over lambda, so that's H over lambda M. So I'm going to go ahead and calculate that. H divided by 0.1 times 10 to the minus 6, and then multiply by the mass times 9.109 times 10 to the minus 31. And I get 7.3 times 10 to the 3. And next, if protons were used, we just basically need to redo these calculations by changing the mass to 1.67 times 10 to the minus 27. So I'll go ahead and do that, and maybe I'll put it on a separate page. So then we'll call this C. So delta V is equal to, let's see what that's, 1.67 times 10 to the minus 27 gives me 8.2 times 10 to the minus 8. What were we swapping for? 8.2 times 10 to the minus 8. So that's really not that much. 8.2 times 10 to the minus 8. I'm going to kind of reflect on these numbers sort of at the end. Volts, and then for the speed, that's just plain V. Again, just redoing the calculation, I get 1.67 times 10 to the minus 27, and then I get 4 meters per second. So maybe the idea is that like that it's possible to see the interference effects of electrons through reasonably sized pinholes, which is probably more the principle along the principles behind TEM microscopes is that you can really see this wave behavior by getting protons to go to a sort of reasonable speed. So 4 meters per second, and then for the protons, and then the velocity of the electrons is actually much higher. Yeah, that's so interesting. It doesn't really make sense that the velocity for electrons has to be much bigger. So I guess this really specifies the momentum in either case, like given that we want a certain lambda. And so because the mass is smaller, the V has to be a lot bigger for the electrons. Interesting.